Alright, we're here with the Chapter 16, Rigid Body Kinetics. Here in this first problem, we have a quarter circular rod that I can assume, and it's moving to the right. The rod has a mass of 2.5 kilograms and is guided by the small wheels. We have a force P that is 8 newtons applied at B, which I need to add that. At B. So we're being asked to find the acceleration in the rod and the reactions at A and B. So first, drawing a free body diagram, we have our vertical components in the A at points A and B, and we know that our component in the x direction is at B is equal to P, so the 8 newtons. The one thing that I still am not sure on is how we find point G here, or the center of mass of this rod. I tried using some of the formulas from statics, but was unable to truly understand where this came from. And so I'll be looking at that in the solution video after this assignment is due. However, we know that the weight is going in the negative y direction at this point, and we can see that calculation at 24.525 newtons, and this is equal to the center of gravity moving to the right, so mass times acceleration at that same distance, 2r divided by pi. So for part A, in finding the acceleration in the rod, we take our sum of forces. The force is equal to ma, so we use Newton's second law, and we manipulate the equation to find the acceleration, plug in the values, and we find that acceleration is 3.2 meters per second squared to the right. And it gets a little bit tricky in finding the reactions, and so to find a y, sorry, there, I also forgot to add in the y there. So to find the reactions, we take the sum of moments at point B, so we get rid of the by and the p force, and so we're left with the weight times the radius minus the distance from point A to the center of gravity, minus ay times r times the radius, sorry about this, is equal to mass times acceleration, as we see in the free body diagram, multiplied by the distance to point B. Manipulating the equation, getting rid of the r's, getting rid of the radiuses, and plugging in the values that we know here into this equation, we find that ay is equal to 3.82 newtons in the vertical direction, as we assumed. Then to find by's, we have already found bx, as it is in the as bx is equal to point P, as stated up here, which I'll actually box that as well. So we have ay plus by minus the weight, and so moving the equation, manipulating it, and putting in the values that we've already calculated, we find that by is equal to 20.71 newtons in the vertical direction. next problem, we have this triangular weldment that is connected at these two slots. We know that the velocity of each pin is equal to 30 inches per second downward along the slots. The slots have a radius of 6 inches and the weldment weighs 16 pounds. So the mass center is point G there. And we are being asked to find the acceleration of the weldment and the reactions at A and B, much like the first question. So in this one, we needed to find use two different free body diagrams. First of the slots, and as it is moving in a circular-like motion, we can use the acceleration in the normal and the acceleration in the tangential coefficients here. Or coefficients is probably the wrong word. Either way, we have the acceleration in the normal direction is equal to v squared over r. So we find that that is equal to 12.5 feet per second squared and 30 degrees in quadrant 3. And as we see from the free body diagram, we assume that the acceleration in the tangential direction is 60 degrees downward in quadrant 4. Using this information, we can move to the second free body diagram of the weldment. And so we have the forces at A and B, both at 30 degrees with respect to the horizontal. The weight moving down from the center of mass at point G is equal to the mass times acceleration in the normal direction and mass times acceleration in the tangential direction, each with 30 degrees and 60 degrees with respect to the horizontal. And so we can find this angle beta with respect to the vertical, and we find that the angle is 24.14 degrees. But before that, we are able to find the acceleration in the tangential direction at 60 degrees as shown. So we take the sum of the forces as we have a weight, mg times cosine of 30 is equal to mass times acceleration in the tangential. And we find that the acceleration in the tangential is 27.886 feet per second squared at 60 degrees in quadrant 4. Now, as we have both acceleration in the normal and tangential directions, we square both of those and add them together, and then take the square root to get the acceleration of the weldment. And we find that the acceleration of the weldment is equal to 30.6 feet per second squared. Now this 84.14 degrees comes from adding 60 degrees plus the 24.14 degrees. Continuing on for part B, as we have mass times acceleration, as we're trying to find the reactions at A and B. So we first need to, I'm still a little curious as to why this mass times acceleration, that we needed that. And so as we take the equilibrium and we set it, trying to find the equilibrium. So we sum our moments about A, and using what we learned in statics as we take point B times cosine 30 times the 9-inch distance minus the weight times 6 inches is equal to mass times acceleration times cosine of 84.14 degrees times the 3-inch distance. And following plugging in the values and doing algebra, we find that our point B is 1.285 pounds, and it is 30 degrees in quadrant 1. And here we can find that we can sum forces in the x direction and do a very similar thing, as we have a cosine 30 plus b cosine 30 equals ma cosine 84.14 degrees. And so manipulating the equation, plugging in the values, and following simple algebra, we find that the reaction at A is equal to 0.505 pounds at 30 degrees with respect to the horizontal in quadrant 1. Hold on, excuse me. My daughter is once again not sleeping, so I'll be right back. Sorry about that. All right, now on to the next question. So here we have two discs, and disc A is moving towards disc B by a horizontal force P at a magnitude of 20 newtons on the axle. We have the static, or the kinetic friction is 0.15 between the discs. And so we're being asked to determine the angular acceleration of each disc and find the angular velocity of each disc. So breaking it down, we take the free body diagram of disc A. Sorry, that should not be B. Sorry, I didn't have time to review this before. So I just take this free body diagram. We have the similar things we've had in the earlier questions, but now we have a contact point C, and so we have a force that is being exerted on that point. And so here we need to use the moment of inertia of a disc. This that should say A as well. Sorry. Okay, so we have the moment of inertia at disc A is equal to 1/2 times the mass multiplied by the radius of the disc squared. And we also can find the force at the contact point as we take 0.15 times the 20 newtons, as that is the normal force as it's pushing back against the horizontal force, 20 newtons. So to find the angular acceleration of the discs, as disc A then influences disc B, as disc B is at rest initially. So we sum moments about A, as we have the force at C times the radius of A is equal to the moment of inertia at A times alpha at A. As here we are looking for alpha, we plug in our values that we have calculated, manipulate the equation, and we find that the angular acceleration of disk A is 12.5 radians per second squared in the counterclockwise direction. Since disk B is influenced by disk A, we find the moment of inertia here, similar to what we did with disk A. Some moments about point B, or about disk B. No, point B, because it's on the axle. Take a similar approach to that, so we can find the angular acceleration of B, and we find that is equal to 33.3 radians per second squared, also in the counterclockwise direction. Continuing on to part B for the final angular velocity. So we were given that the initial angular velocity of disk A is 360 RPMs in the clockwise motion, or clockwise direction. And so setting that in something that we can work with in radians per second, we find that it is equal to 12 pi radians per second. And using the free body diagram of disk B, So we have the normal force moving opposite to what it was for the free body diagram of disk A, as well as the force of the contact point C. So we designate that as F sub C prime. So as we set those equal to each other, that is essentially setting omega A times radius A equal to omega B radius B. Plugging in the things that we know. So we need to solve for time, for the time that it takes to reach this final velocity for point A and B, or for disk A and B. So as we have omega A is also equal to omega naught at A minus alpha A times T multiplied by radius at A equal to alpha B times T times radius at B. Plugging in those things that we know and what we have calculated from part A, we are able to break it down to the equation of omega A is equal to omega naught of disk A minus alpha A times time. Oh, I skipped a step. So time, following this earlier equation, we find that t is equal to 1.0053 seconds. So to find the final angular velocity, omega A, we plug in the 12 pi minus the 12.5 radians per second squared that we found for alpha of disk A. Multiply that by the time, we get 25.13 radians per second. Then converting that back to RPMs as it was initially, we multiply that by 60 over 2 pi, and we get omega A is equal to 240 RPMs in a clockwise direction. Similarly, we do the same thing for omega B, and we find that omega B is equal to 320 RPM in the counterclockwise direction. The next problem, we have a drum of radius 200 millimeters that is attached to a disc of radius 140 millimeters. They're suspended by two separate cords having two separate tensions, as denoted here. So we're being asked to determine the combined radius of gyration of the disc and drum. So from the book, we are able to find this equation for radius of gyration, or K is equal to the square root of moment of inertia divided by the mass. So drawing a free body diagram of this, of the drum and disc, then setting that equal to so our mass times acceleration from point G. Oh, this is kind of odd, but it is moving in the vertical direction, and so our mass, or the 5 kilograms that this entire system weighs, is moving in the positive y direction, and we have the angular direction of I times alpha. So we can calculate the weight, in essence getting the acceleration and how that is moving as we sum forces in the y direction. That is equal to the 60 newtons from the two tensions in the vertical minus the weight plus the 5 kilograms times acceleration times A, also moving in the positive y direction. Manipulating that and solving for A, find that the acceleration is 2.19 meters per second squared in the vertical direction. We also know that the acceleration is equal to the radius times alpha. So the angular acceleration is equal to 10.95 radians per second squared, moving in the clockwise direction. To find the radius of gyration, however, we take the sum of moments at G. We set that equal to the tension at A times the radius, or times the horizontal distance to G, subtracted by the tension at B, also times the horizontal distance. As the sum of moments at G is also equal to moment of inertia times alpha, we plug in the values for the right side of the equation. And then moving up here, we also, as you can manipulate that same equation, we find that moment of inertia is also equal to k squared times the mass. And so plugging that in here for moment of inertia, we take the k squared times m times alpha is equal to 1.6 newtons per meter. So then plugging in our values here, we're able to solve for k, and we find that k is equal to 170.9 millimeters. And the next problem here, we have a slender rod that is being suspended at hinge C using our moment of inertia equation. 1 over 12 times the mass times the length squared, and acceleration is equal to radius times alpha. So we're being asked to determine the angular acceleration of the rod and the components of reaction at C. Again, free body diagram, assuming the directions of our components, setting that equal to our mass times acceleration and the moment of inertia times alpha. We take the moments about point C to get the angular acceleration of the rod. So we have the point P, or the force P, multiplied by the length, 1L over 2 plus the radius R, minus MA times R minus I times alpha, is set that equal to 0. And as we manipulate the equation and plug in the values that we know and are given, we find that the angular acceleration of the rod is 107.1 radians per second squared. As at point C, there's no horizontal component. Thus we solve, there is a horizontal component, and we know that the vertical component, Cy, is equal to the weight. So we have Cy is equal to 39.2 newtons. And as we sum forces in the x direction, we have Cx is equal to, or Cx minus P minus MA equal to 0. Manipulating and plugging in the values that we know, we get that Cx is equal to negative 21.4 newtons. Thus, Cx is equal to 21.4 newtons to the left. So our assumption, as it is moving to the right, was incorrect. Alright, moving on to the next one, we have a wheel on an incline here. So we're given the radius of gyration at k. We're being asked to derive an expression for the acceleration of the center of the wheel in these terms. As we have before, free body diagram of the wheel, setting that equal to the mass times acceleration of the wheel. Then as we sum moments about the contact point C, we have the weight multiplied by sine of beta times the radius is equal to the mass times acceleration times r plus moment of inertia times alpha. Plugging in the what we're being asked to answer in terms of, so we have mg r sine beta is equal to mr alpha times r plus mk squared times alpha. Manipulating the equation, doing some simple algebra, we find that alpha is then equal to gr sine beta over r squared plus k squared. As we know that acceleration is equal to the radius times alpha, and as we're looking for the acceleration, we manipulate the equation and we find that the acceleration is equal to r squared times g times sine beta over r squared plus k squared. In the next question, we once again have a drum of radius 4 inches that is attached to a disc of 8 inches, of an 8-inch radius, and is being pulled with a magnitude of 5 pounds in the vertical direction. We are given a static and kinetic coefficient of friction, as seen here, and we're being asked to determine whether or not the disk slides, and the angular acceleration of the disk and acceleration of g. So again, free body diagrams, as we've been doing before. We have a contact point C, and as we have using these equations here, so as the disk rolls, we have the acceleration is equal to the radius times alpha. So we take the 8 inches and we convert that into feet as we divide the 8 inches by 12. And so acceleration is equal to 8 over 12 times alpha. The moment of inertia is equal to mk squared. So as we plug that in, and again, the radius, converting that to feet, I find that this is the moment of inertia in pounds per foot per second squared. And putting that into some moments about point C, as it gets rid of 2 forces. So we have the 5 pounds times the radius, 4 over 12 feet, is equal to the mass times acceleration times the radius plus moment of inertia times alpha. Plugging in the values, we get alpha is equal to 7.73 radians per second counterclockwise, and we find acceleration is equal to 5.152 feet per second squared to the left. Continuing on, are a few other things here. So to find if the disc slides, we have to determine the force F as we have in the free body diagram. And so we find the force by doing mass times acceleration. So we have the force is equal to 1.60, and the normal force is 5 pounds in the vertical direction. So using force is equal to mu k times n. So the force is equal to 1 pound. However, using the so if the force is greater than that's where it is. Okay. So using the static friction, we know that the force is larger than the static friction, so the disc does slide. And having the angular acceleration of the disc, we use some moments about point G to find alpha. Plugging in the values, we find that alpha is equal to 12.88 radians per second squared in the counterclockwise direction. Likewise, using F equals ma for the acceleration of G, we find that the acceleration is equal to 3.22. We find that the acceleration is equal to 3.22 feet per second squared to the left. So here, this is the last question. So we have two discs being connected by a uniform rod. A mass 2.5 kilograms. We have a counterclockwise couple moment of 2.25 newtons per meter. And we know that the disc roll without sliding. So we're being asked to determine the angular acceleration, or the acceleration of the center of the discs, and the horizontal component of force exerted on disc B by the pin D. So we have we have all of our given values here, and a couple of equations that we may need to use. The moment of inertia equation of a disc, and the acceleration as we've seen before. So free body diagram also as seen before with what we have. This one is a disc A, and so this needs to be done in two parts, so disc A and disc B. And so summing the forces, summing the moments at point E, which is our contact point for disc A, we have the moment minus the pin C multiplied by the distance of 80 millimeters, or 0.08 meters, is equal to mass times acceleration times r plus moment of inertia times alpha. Again, plugging in the equations that we were given up here to the just under the diagram, and plugging in the values that we have been given, manipulating and doing some simple algebra, we find that our first equation is 2.25 newtons per meter minus c times 0.08 meters is equal to 0.0432 kilograms per meter squared times alpha. So keeping track of that equation, we then move to disc B and do a similar steps here. So as we take the moment of point H, which is the contact point for disc B, we have the pin D that is also 0.08 meters from from the contact point equal to mass times acceleration times the radius plus moment of inertia times alpha. And so manipulating that, adding in the equations, we find that our second equation is d times 0.08 meters is equal to 0.0432 kilograms per meter squared times alpha. A third free body diagram is that of the rod. And so we know that both of the horizontal components, the pins, will equal each other, but also with the moment moving counterclockwise on disc A, we know that the mass times acceleration of the rod will be moving to the left. And so we can find the acceleration of the rod by setting acceleration of C, which is, well, the acceleration of the rod is equal to the acceleration C, which is equal to acceleration of disk A plus acceleration of C with respect to A. And so plugging in these values that we know, the 120 millimeters minus the 0.04 meters, which is the distance from point C to point A, times alpha, we have the acceleration of the rod is equal to 0.08 meters times alpha. Using equilibrium, we have C minus D. So we have the MA of the rod is equal to 2.5 kilograms times 0.08 meters times alpha. And so we have our C minus D is equal to 0.20 kilograms per meter times alpha. And continuing on, transferring over the first two, or these three equations. Now, coincidentally, that the third equation, the C minus D equation, we were able to manipulate both equations 1 and 2 to set them up for C and D. So using that and plugging them into this C minus D equals 0.2 kilograms per meters times alpha equation, we're able to find alpha through all of that, all these numbers and simple algebra. We find that alpha is equal to 21.9726 radians per second squared in the counterclockwise direction. And as before, at the beginning of the problem, we had this equation. The acceleration is equal to the acceleration at A equal to acceleration at B is equal to the radius times alpha. So as they are both the same radius, 0.120 meters, so we multiply that by the alpha that we just calculated, we find that the acceleration of the disks is 2.64 meters per second squared to the left. Now part B, the horizontal component of force on disk B by the pin D, we use the D equation up here, and the alpha that we calculated just a few steps ago. Plug in those values and do simple multiplication and division. We find that the horizontal force on disk B by the pin D is equal to 11.87 newtons to the left. Again, sorry this is so long. So thanks.